Welcome back, everybody, to the Across the Sky podcast, our Lee Enterprises National Weather Podcast. We are in April. You know what they say, April showers bring May flowers, and we're going to talk about flooding in this episode. That's why we get too many April showers. But before we get started on our interview, we're going to toss it around the horn here. We have Sean Sublett at the Richmond Times-Dispatch, Matt Hollander in the Midwest. Kirsten, we're going to say she might be able to join us halfway through this podcast. If not, it's just going to be three of us here and our guests. Guys, it is April. Matt, you're just as busy as ever weather-wise here. Let's forget about the weather, though. How's everything going in Matt Hollander's life?
Yeah, I could go on and on about how I just do not catch a break with these storms. I mean, we've gone from winter to severe weather season, and actually a little bit of both as of this recording on March 30th. It looks like some heavy snow in northern Wisconsin, but severe storms in southern Wisconsin. They might end up with a little bit of snow in southern Wisconsin. So yeah, the active weather continues, but overall, I'm doing good. It just seems like, man, my little spring break trip seems like a distant memory now because it's been right back to it. Nonstop things to talk about in the Midwest from a weather perspective.
Gotcha. Sean, what's happened, my man? I don't get to talk to you all the time now that we don't do Snow Search on Mondays anymore.
I know, but we're going to be doing some other things this summer. So as they say, stay tuned. But,
right.
Otherwise things are reasonably quiet here. The big story here in Richmond, we've got race weekend. NASCAR's tour is coming through Richmond this weekend. Very excited for that. For Sunday, it's going to be gorgeous here. I mean, around 60, 65 with sunshine for the race here. But before that, it's going to get really warm and windy. A little freaked out about how windy it's going to be this coming Saturday. So we'll see how that all plays out. But otherwise, we're talking about flooding and droughts and flooding and how, California has suddenly just, their drought is almost gone. But it started to get a little dry here in Virginia just in the last 2 or 3 weeks. So that's something we're going to have to watch very closely. Getting into April, the sun angle gets higher in the sky, it gets warmer, ground dries out faster. So that's kind of one of those things in the back of my mind as we get into April.
Yeah, you bring up drought, and I was actually just looking at this earlier today. So this is like the March 28th update from the United States Drought Monitor. In the West, a year ago today, 88% of the West was in some stage of drought. And after, I think it's a dozen of these atmospheric river events and 400 inches of snow in Lake Tahoe, we're now down to 35% with drought. So a huge chunk taken out over the past year. Still got a ways to go. The West is always fickle with this, but really a tremendous dent in that drought. And yeah, so I know you guys in Virginia, you guys are kind of teetering on drought. We're doing the same here in South Jersey. As we like to say here, it could rain overnight and you could have a fire in the Pinelands that day because we have that strong sun. We got this, what we call a sugar soil in the Pine Barrens here, where it's really just sandy soil and think about the beach, you dump water, it drains right through, kind of the same concept. So we're in peak wildfire season as we go into April and May. Rain is a good thing. I think Luke Bryan sang about that once, how rain was a good thing. So we're hoping for rain, but what we don't want is too much rain. And that's where our guest comes in for today here. We're going to talk about flooding forecasts, flooding in real time, block by block, because sometimes we do need it. And especially just a little side professional story here at the Jersey Shore. We do have a number of resources available for people when it comes to coastal flooding. That's what the tides. We're going to talk a little bit more about rainfall flooding here, mudslides and all of that. And here with me is Valeriy Ivanov. He is professor, of hydro systems engineering at the University of Michigan here. He wrote all about this machine learning method that kind of can make this all possible. So we are going to welcome him onto the podcast. Good talking with you here today.
Hello, everybody, and thank you for having me in your podcast.
Awesome. Yeah, pleasure to have you on here, especially as we get into the spring. So, it was interesting. You wrote that back in January of 2023. You were checking these forecasts on your weather apps, on your cell phone during these weeks of intense storms. And we're wondering if these same people who are in the downpours were using this technology to decide whether or not they need to leave and evacuate in California. So just kind of give us a little more detail, walk through us, what you were thinking, what you were feeling during that time, and how it comes into some of the research that you are doing now.
Well, it follows sort of the research that we've been doing for, many years now. I think about 8 years ago, we started asking this question: what would it take to produce flood forecasts at the scale or at the resolutions that would be most useful to people? I think at that time, we looked at, specifically, we looked at the Nashville 2010 flood. I don't know if you remember that, but some people called it a 1,000-year flood. There were multiple fatalities, about 26, 27 people died. And at that time, when we started looking at the causes or the reasons for why people died, I mean, it was pretty much the ignorance or the lack of knowledge of where the flood was happening. So every time when I would open a talk on the topic of flooding at that time, I would show a picture from National Geographic, two teenagers holding to a stop sign. And the stop sign is really like at the level of where they're holding to not be washed down by the river. And the story goes like this: they went to church, they did not know what was happening, they took the wrong turn, and they ended up in the river, almost dying in this incident. And so that kind of like triggered the thought: well, we don't have these forecasts, we don't know where the floods are, why, and what it would take to actually produce them. And we started looking at that problem. We started piecing things together, which is models, data, forecasts, computational resources. And we quickly realized, well, yes, we can simulate floods at a very high resolution, at a very high level of detail, but they're not computationally feasible. And by not computationally feasible, I mean, if you have a flood that, say, lasts a day, it would take about 3 days to maybe simulate that flood, right? So if you're talking about decisions that need to be made within an hour, within the next few hours, you're way late. You're way too late to produce that forecast. And so that is how we kind of started thinking, well, there should be some alternative solution to the problem. And this is where we started looking into probabilistic methods developed by the Department of Energy, actually looking also at the very computationally intensive problems that they don't need real time, but they really have to get the computational intensity.
This reminds me of the very early days of numerical weather prediction, where the computers were not strong enough and you could do a forecast mathematically, but it would take you 5 or 6 days to do all the calculations for a forecast that was 12 hours from now. So are there any ways you can make some shortcuts or do some parameterizations to give you a head start on this problem, like knowing where some of the, just understanding the general topography of an area, where there is low-lying creeks? Or is that a way to kind of get a jump start on this process?
Yes, and it's exactly how you're describing this, Sean. This is exactly how people started thinking about this problem. Can we take simpler models? Can we, instead of producing a flood forecast in terms of inundation, velocity, pressure, can we produce a flood forecast in terms of flow rate at a nearby stream gauge? And that's how the National Weather Service is operating. This is how the Office of Hydrology is producing flood forecasts for like 2 million reaches nowadays. It's flow rate. It's not water level. It's not flow velocity. And actually, to us, I think these are the things that matter. If I walk outside of my house and I am in a car, I don't need to know the flow rate in the river, because that's a far-fetched extrapolation, if you will, right? Yes, you can use topography, but then topography is to sort of like extrapolate away from the river and to know where water would be. But as you understand, of course, that brings uncertainties. And flood forecasting is already uncertainty-laden problem. We look at precipitation forecasts as highly uncertain. Some time ago, we looked at, well, even the data that go into a flood model being highly uncertain. Nowadays, it's kind of getting better. It's a data now rich environment. But why would you want to add an additional uncertainty of extrapolation if your problem is already uncertain? And so that's why we kind of went with what we call high fidelity model solution, which were which are numerical hydrodynamic models that were developed back in the 70s and 80s, is just to realize that they are not real-time ready. And you have to create a bridge from these complex solutions that give you everything that you need: flow velocities, inundation levels, pressures, you name it. But how do you create a bridge to something that's much, much faster? This is where the machine learning came in.
And I'm curious, how detailed can you get using these simpler models? And then how much more quickly can you run it? So hopefully we can get as much detail as possible. Then how much more quickly using this new solution is it compared to the way things are now?
We published a paper a year ago in Geophysical Research Letters, and that's how kind of where this conversation piece came from. That shows that if you do everything carefully and you can try to map the solution of the high fidelity model to the machine learning informed solution, you can cut 7 orders of magnitude from computational time. 7. So when I was saying you would need to take 3 days to simulate a 1-day flood, now you can do it in a fraction of a second. And you don't need to have a computational center. You don't need to have HP, high performance computing cluster available at your capacity, which, by the way, who would have that during the flood? So the idea was, can we take that difficult problem and map it into something that's actually available to a typical flood forecaster, which is a desktop, and it's not going to be a HPC desktop, so that the forecast can be carried out in a matter of minutes. And in our case, again, we are showing it's possible to do it within seconds.
So if you do this in minutes, in seconds, like where do you see this information going? Like if I'm living in this flood area, how will this get to me? And what do you think, or how would you want it to look like? Because you need, we have all this, which is great, right? But we need it to get to the end user, who is a person who lives in their house in California where there could be a mudslide or some kind of significant flood that day.
The big picture behind this is you take your cell phone, you take your gadget, you open an app, and you type in your neighborhood, and you get a flood forecast. When we started looking at that problem, and again, it was about 7 or 8 years ago. I don't know if you noticed, but I definitely did. At that time is when we started looking at weather forecast. You started getting precipitation with uncertainty. It's still not exactly my neighborhood, but it gives more information now, right? And that's kind of like what we wanted to get to. I type in my address and it shows me how the flood is going to look like in the vicinity of my neighborhood, and it would give uncertainty. Uncertainty was a big also a part of the problem that we were trying to solve. And the framework that we proposed, and we show that it works, brings not only this high resolution, real-time prediction of the flood information, but it also gives uncertainty associated with that. So the big picture, again, going back, is at some point, you will have a map on your phone that will tell you, this is where the flooding is, this is where there is a big uncertainty, and then you make the decision based on that uncertainty, based on that flood map, on what you do.
Awesome. We're going to take a quick break here. We'll be right back with the Across the Sky podcast.
This Memorial Day weekend, it's the 3rd annual Healing Field of Honor sponsored by the Winchester Rotary Club and True North Group. Over 1,000 flags will fly in solemn formation at Winchester's Handley High School. Dedicate a flag to a loved one, a veteran or local hero, and the flag is yours to keep. Visit the Field of Flags anytime Memorial Day weekend and attend the closing ceremony May 29th at 3 p.m. For details and flag purchases, go to RotaryClubOfWinchester.org. Seating is limited, so feel free to bring a chair.
Welcome back, everybody. We are here with the Across the Sky podcast. New episodes come out every Monday. You can get that wherever you get your podcasts or at your favorite news site here. It might be the PressAtlanticCity.com, might be Richmond.com, or in Matt's got like 30 of them. We could be here all day chatting about all the websites that he covers. We're here with Professor Ivanov. He is with the University of Michigan. We are talking more about flooding here, real-time forecast. Professor, you said that, ideally what we would have is someone opens up an app on their phone and they see the level of risk for their block, really, and how much it's going to flood here. Now, we talked a lot about rainfall flooding. I do want to talk about coastal flooding because we do actually have a lot of this already on the coastal flooding level. If a tide gauge is this many feet high means that these blocks are going to see water here. So I'm curious, tell me what the difference is between, doing this with coastal flooding and then, we'll say precipitation flooding. And then talk to us also about, hey, I'm here in South Carolina, a hurricane's coming. We usually get coastal flooding, but now we got all this rain. How can what you're doing help those situations?
Yes, and I would say that the problem of flooding, or sort of the conceptual differentiation between different types of flooding, it's perhaps more of a philosophical type rather than the actual one. Because if you look at coastal flooding, the storm surge, it's the same type of equation that describes flooding. So yes, the sort of the initiating agent is different. So it's a massive body of water that sits near the coast. But as the flood propagates inland, it is the same type of equation that sort of serves to predict the flooding. So my background is sort of physical hydrology and hydraulics. So I typically work on land. Can the same type of machinery, can the same type of mathematical approach be applied to a coastal surge problem? Yes, absolutely. And we are already looking into into that direction. Sometimes when you talk about coastal areas, I mean, the floods that happen are not caused actually by a single type of mechanism. If you have coastal surge, yes, people talk about coastal surge, but typically these types of floods also are associated with the massive amount of rainfall that occurs over the land, and that brings the land portion, or what we call fluvial flood or groundwater flood. Is it possible to address the problem in the same fashion as we've done it for an urban environment in Houston, where we looked at the land, or like the fluvial and pluvial type of land? Yes, absolutely.
Going back with, I think you were talking to us a little bit about, a hurricane coming through, right? That's coming through, whether in the south or in the east, and you got that, and you talked a little bit about probabilistic learning. You said in your piece, you said it's a type of machine learning. All right, so explain to us what probabilistic learning is to the layperson, because I'm not familiar with it really too much either. And how is that differ, or how is that a part of machine learning that we're hearing about, all the time?
Typically, hydrologists and river or hydrologic forecasters, they used to deal with what we call numerical models that describe a set of processes that lead to flooding. And these are, first principles based mathematical models, which is conservation of mass, conservation of momentum. They're, of course, used in numerical weather prediction. And these are the ones that we call physics-based, comprehensive, high-fidelity type of models. But these are the ones that create a challenge of computational effort, right? So these are the ones that are very difficult to compute. However, with the advance of, computations, people started looking at, what's called machine learning-based approaches. And these are not based on the same principles. They are, in fact, fairly simple functions. And these functions have coefficients that can be trained. And sort of the technical jargon is, you can take a solution of a very complex model, a high fidelity model. You can produce many, many outputs from that high fidelity model. And then you can take a simple model, a machine learning model, to mimic that solution given the same type of forcing, if it makes sense. If you took calculus, which of course you did, what we are taking is, we are taking a hydrodynamic model and we are representing its solution with a set of polynomials. And what happens with these polynomials, you need to match coefficients. You need to match coefficients, and these coefficients will produce this nonlinear behavior of a very complex model. And this is done through the phase of training. So what we emphasized in the research paper that we published is that there is, of course, a training period, and it should not be sort of neglected. Before you get to the real-time flood forecasting, you need to train the simpler models. But this does not have the pressure of time. You can do it when you have a drought, when there is no flood. And essentially what it boils down to is, you take your hydrodynamic high-fidelity model, you run it multiple times, multiple number of times. Like, for example, in the paper, we ran it 10,000 times. And then you look at the output and you train your machine learning approach to mimic the solution. For example, inundation at location X, Y at time T0. You can train another model to reproduce model behavior at yet another location. You can take any output from the high fidelity model and train your solutions for that. Do you want this to be inundation level? You can do it. You want to have a discharge flow rate? You can do that. You can do some statistics based on that. And again, the trick is you go away from differential equations that take a lot of computational time. You go to something that's trivial, mathematically trivial. That's why when you have a trained machine learning model, it takes really a fraction of a second to compute a solution, because it really is one line statement in your code. Does it make sense?
Yeah, it's pretty complex stuff, but fascinating at the same time. And what I want to do is kind of go back to the inspiration of all this, because what stood out to me, I was reading your article, and you mentioned that you had a near drowning experience while crossing a river once. So could you tell us a little bit about that story? What exactly happened, and how did that inspire you to do this work?
I was much younger. I was about maybe 25, 26, and I was in a backcountry trip with my buddy, and it was in the middle of what you call the middle of nowhere. It was actually in Siberia, and we hiked out. It was about maybe 30 miles from the nearest settlement, and then we came across a river. And the river was actually in a state of flooding at that point. Maybe before I actually tell you this story, I can tell you that when we were coming back on a truck, people told us that this river, at about the same time when we tried to cross that river, it upsided a huge truck that was about like 15 tons of weight. So us, me hydrologists who should have actually appreciated what a flowing force, what the force would be from the flooded river, we decided to cross it. It was like either you go back where you started or you actually get to your final destination. So we decided to cross the river. And as I started wading into the river, at some point I was, taken by the current. I was also flipped with my backpack. I had to struggle to get to the other side. And I remember just shivering, being on the other side. And then my friend who remained on the other side of the river, he tried to cross it, even though I started shouting, don't, like you walk on that side, I'm gonna walk on that side. He started shouting, he started drowning. I dropped my backpack, I ran into water and tried to pull him out. Everything ended well, obviously, but it created this understanding of how ignorance about what this force really is, how impactful that might be. And frankly, again, if you never were in a current of high velocity and of high depth, you may not really appreciate. And that really, I think, explains that about 2/3 of fatalities associated with floods in this country, they are classified as walking in water or driving in water. It happens every year. Again, it's 2/3 of fatalities.
Well, you know what they say? They always say, turn around, don't drown. That's always the big campaign, with any kind of flooding. I'm curious, though, like how wide was this river? Like how deep and how wide are we talking with this river? And why Siberia? Are you from Siberia? Is that part of Russia you're from?
Yes. Actually, it was about, you see my background right now, which shows a large forest that's in the polar Urals. And the place where I almost drowned was about 400 kilometers south of that place.
Okay.
And yeah, it was just, we used to do a lot of backcountry trips back then. I was a student, very interested in nature and learning nature. And yeah, the river was maybe not that wide. I remember it was maybe around 200 feet wide. In terms of depth, I'm about 6 feet tall. But when it took me, I stopped feeling the bottom of the channel. So for a fraction of it, I was just taken by the river. I could not feel it, and then I started getting hit by rocks, and yeah.
That really is amazing. And to your point, Val, I agree that until you've experienced it and have a firsthand experience of being in current that rapid and to that depth, it's really hard to understand how much power that moving water truly has on whether it's you or on a vehicle. And with that, regarding safety, and we talk about downscaling the model so they end up just being one line of code so you can get them run pretty quickly. What do you think that's going to do in terms of lead time for a flood? I mean, are you hoping this goes to a place where you have a flood forecast based on rainfall that's expected in the next 20 to 24 hours, or rainfall that is expected in a much shorter time frame? Ideally, how far in advance do you think you could give people some kind of a risk assessment of what the flood potential would be?
Yes, great question. And of course, that's actually the key. I mean, it's the rainfall or precipitation forecast is key to any flood forecast effort. And I think what stimulated our effort is that some time ago, NOAA started producing precipitation forecast with something that's called high resolution rapid prediction system, which produces precipitation forecast 24 hours ahead at about 3 kilometer resolution, 1 hour temporal resolution, which, okay, well, yeah, it's not going to be super accurate, but it's going to improve over time. And by the time when it becomes very good, at that time, you should be ready. And so I think right now, realistically, in this country, we can do 24-hour lead time forecast that you can also update, right? As you get near the storm, and as the storm starts happening, your forecast for the next few hours is becoming more accurate. And you can update your solution. And it's not going to take any effort, as I explained.
And how close do you think we are to making this operational? Like you described somebody pulling up on their phone and looking at a map to see which roads are going to flood. Like how far away are we, do you think, from that being a reality, that you could pull up an app and see which roads are going to flood? How close do you think we are to having that happen?
Another great question. Well, I came to this country 25 years ago, and I was hired on a project funded by NASA, and the title was something like High Spatial Resolution Flood Forecast or something like that. Are we there 25 years later? No. Why is it not happening? I cannot judge. But I think we have all the ingredients that are available to us that can make it happen. At least it can start happening in some very specific environments, such as cities, right? I mean, you take New York, you take Boston, you take San Francisco, you take Houston. I mean, cities that have sort of a higher risk associated with floods, or that have a history of floods, and you can start implementing it there. Can we do it? As a research group, yes, we can do it. I mean, we used to joke that it would take about $5 million to do it, but of course I understand it's a little more than that at the national scale. But again, I think that all the ingredients are actually available nowadays to start making this happen.
The idea that somebody could pull up an app on their phone and see which roads are going to flood, I think that would do so much. Instead of people venturing out, we talk about there could be flooded roads out there, but we can never pinpoint exactly where. Sometimes we know there's certain roads that do flood more often than others, low-lying, poorly drained locations. But to be able to give people more confidence and be specific that even before somebody has to encounter one of those flooded roads to report it, knowing that it's already flooded would be so helpful and so useful. I know just from a broadcast perspective, we could come up with a list of roads, like these roads are flooded, and we get that information out to people as quickly as possible. I think it would be less likely that anybody is going to, ever risk, before any barricades can be put up, we can avoid the risk of anybody accidentally driving into one of those flooded roads. So I look forward to the day when that app is available on the phone, because boy, I think that could do a lot to save some lives.
Yes, I think providing information to people is really crucial, and providing information with uncertainty is even more so crucial, because people can make decisions. I honestly believe people can make rational decisions.
Well, with that, I believe we're going to wrap it up here. Great conversation about flooding. And we're looking forward to, again, putting that in the power of people's hands, with a flooding forecast like that on an app or whatever it may be. And even for us as meteorologists who are communicating that info to the public, that's all good as well. Anything else before we wrap on up here for today, Professor?
Well, thank you very much for this fun conversation. And yeah, I'm just like you. I'm looking forward to this happening at some point. Awesome.
Wonderful. Well, we are going to wrap it up on the other side of this break. Thanks for listening to the Across the Sky podcast.
Michael J. for Hope for the Warriors. Started back in '06 at Camp Lejeune. Military families witnessing the effects of war on their loved ones. Now, almost 20 years later, they've aided over 53,000 service members, veterans, and families with confidential, high-quality behavioral health care services at little or no cost to post 9/11 vets and their families. Over 91% of every dollar donated goes directly to the programs. If you're as concerned about our heroes as I am, go to hopeforthewarriors.org.
So that was Professor Ivanov. Happy to have him on. And we're happy that one day in the palm of your hand or website, if it's raining, significant rain, severe rain, you'll be able to see if your block is flooding. And listen, I get it. I know a lot of us, we might be living, in suburbia or a city where, you might not flood all that often, but there are some of you who are probably listening where flooding is an issue that you have to deal with several times a year. And this is where it's really going to be handy.
Yeah, it's one of those things where sometimes you don't know you're in a flood prone area until it actually floods. I didn't know as a kid, I'm not paying attention to that stuff. It's only within the past 10, 11 years, I'm outside, I'm looking at an environment, whether it's urban, suburban, rural, and I start looking for divots where water can collect. I kind of see beyond the buildings and I'm like, oh, water could collect there, water could collect there. I don't think I want to build a house over there because it's toward the bottom of a hill. I don't think I really want to do that. So yeah, but if it doesn't get to where you are, you have no idea that it might get there.
Well, I'm glad we're making progress on this because this is a huge challenge because there are just so many elements that are involved with this. As he mentioned, you got to start with the precipitation forecast.
Yeah.
And that is, as with all of meteorology and all of our forecasts, has gotten better, but to be able to pinpoint where the heaviest rain is going to occur, we can now have gotten very good about highlighting areas that are likely to flood. And we can say flooding is likely in this area, but where exactly in that area is the flooding going to occur? That's the challenge. Where is those highest rainfall amounts? Where exactly are those occur? We've got to get better at that. But then also it's figuring out just on the micro scale, it becomes issues like, is a storm drain clogged or not? Because that really becomes an issue, after the fall and all the leaves. Is an individual storm drain clogged? Because if one drain is clogged, suddenly a road that normally wouldn't flood can, if the heaviest rain happens to fall there and they have a clogged storm drain. So there's so many, moving elements to this, and it takes a lot of computational power. So developing a method like this, where the computers aren't having to work as hard and they can be run faster, processing all this data, that's progress. We're moving in the right direction, and being able to say which roads specifically are going to flood. That would be huge. That would be, as they say, a game changer. So
yeah, but even by his own admission, he knows that it's still probabilistic forecasting. In other words, it's still not 1 or a 0. It's not like this is going to flood at this time to this level. It's still probably going to be kind of like this bell curve, or like, this road has a 70% chance of flooding tomorrow. This one has a 20% chance of flooding tomorrow. That's probably where it's going to be, at least initially and for a while, because of just so many uncertainties. Like you said, Matt, to try to quantify every single solitary thing is going to be difficult at best. So I think the best we can hope for, at least for a while, is probability forecasting, like a lot of precipitation forecasting is, for that matter.
When it comes to flooding too, like you said, Matt, it could be just a storm drain, as simple as that. That changes things. I remember a young Joe, maybe not 25 years old, like real young Joe. I used to sometimes put leaves into the drain at my house because I thought maybe I'd get a school, a day off from school if I thought it would rain hard enough. I was so closed-minded to the world back then. But we do hope that this does come into the palm of all your hands, and ours as well, as we talk. And it's all about better communication with weather, and we'll keep saying it until no lives are lost in any kind of significant weather event. All right, so Sean, we're going to pitch it over to you for a second because we have a serious topic coming up as we go into our next Across the Sky podcast, which everyone will be able to check out next Monday.
Yeah, so as I'm sure most people know about the devastating storms, the tornadoes in Mississippi about a week or so ago. A colleague of mine works on the air as a meteorologist in Tupelo, Mississippi, WTVA, Matt Laubin. And we're going to have him on next week to talk about the process, talk about not just being there in the moment, about trying to walk people through a devastating environment in real time, but then how do you deal with it afterwards? There's the initial loss of life, right? And then assessing what has just happened in the coming 24 hours. But so oftentimes, unfortunately, these things kind of get forgotten about at the national level or through the national conversation after a week or so. So we're going to talk about all those things, mental health, what all is involved in that next week. That's Matt Laubin from Tupelo, Mississippi on our podcast. Very, very much looking forward to having Matt on.
We're going to try to, just as a philosophy with our podcast, we have something significant happening weather-wise, we try to talk about it as quickly as we could. So, we'll have him on and, we'll go from there. So we will sign off for this edition of the Across the Sky podcast. Make sure you can subscribe. We have this literally wherever you can find your podcast. So go there, hit the subscribe button. We'll have new episodes every Monday. Hope everyone has a great week, and we'll talk to you soon.